Here we go. All right, so we've been talking about this idea of osmolarity. And again, part of the reason, a big part of the reason you got to worry about osmolarity is because you want your cells to be happy, right? You've got like here's some cell. Most of your physiological fluids, inside and out, are about 0.3 osmolar. So I'm going to just write that out. This is important. This is a number you need to know. You could also write it as 300 milliosmolar. And it's around there. Sometimes people say, 280 to 300. You know, so somewhere around there. But if you have a cell, let's say it's like one of your blood cells, if you have the same amount of osmolarity inside and outside, what's going to be the net movement of water? If you have the same number of particles inside versus outside, and this is my cell membrane, what is the net movement of water going to be due to osmosis?
Basically zero.
What's that?
Zero.
Zero, exactly. If you have a balance in the osmolarity inside and outside, there's no net movement of water in or out. Water there'll be in an equilibrium. There will be water moving in, but for every one that moves in, one will move out. So this thing is not going to inflate or shrivel up. What happens if I took a cell, and again, my cell is always going to be 0.3 osmolar inside. Let's say I put distilled water. What is the osmolarity of just pure water? If I have pure water with nothing dissolved in it, how many moles of particles per liter do I got?
Three.
Is it zero?
Oh.
Say it again.
Is it zero?
Zero, yeah. So distilled water would just be zero osmolarity, right? Because there's nothing dissolved in it. There's no particles per liter of. So if I have zero outside, but I have, my 0.3 osmolarity inside, which way is the water going to go?
In.
It's going to go in. It's going to go from, basically you can kind of think, we'll talk about this in more, but I always think of like kind of the saltier places sucking up the water. Water tends to get drawn into the higher osmolarity. So this is going to actually probably pop. So water comes in. What if I took this cell and I put it in, I don't know, let's say 0.6 osmolar outside? So there's more stuff dissolved outside than there is inside the cell. What's going to happen?
Water is going to move out of the cell.
Yeah, this is going to shrivel up as water leaves. So it's important that the outside of the cell is balanced to 0.3 osmolar, or else the cell is either going to blow up and maybe explode, or it's going to shrivel up like a little raisin. So, the question I have for you: what percent NaCl saline, would you use for an IV flush syringe? So when people have an IV line, They have a little syringe filled with saline, with water, salt water, and they just shove it up into the vein to kind of clear out the line. If you shove that up into somebody's veins, you want to make sure that you are not creating a situation where their blood cells are going to explode or shrivel up. This is just called saline, is the other word for. So let's work this out together. What is the given? What do we know? Given from what I was just saying here, if I want to make sure that this saline that I am shooting up into their veins is gonna be the appropriate concentration to make sure their cells are happy, don't shrivel or explode, what does that saline need to be?
0.3 osmolarity.
Exactly. Did everybody hear Raina? That's going to be our starting point for everything here. We know that no matter what else, this has to be so this is going to be my starting point. Eventually I need to, so I'm going to write that down. By definition, what does 0.3 osmolar mean? It's going to be similar to what we were doing with this dimensional analysis. What's the definition of osmolarity?
Number of moles of total particles over a liter solution.
And since it's 0.3 osmolar, what would I write here?
It's 0.3 mole of the particle.
Per?
Liter solution.
Exactly. So this is where I'm starting. This is where I'm starting because I want to make sure that I'm 0.3 osmolar, and 0.3 osmolar, when we get down to it, it means 0.3 moles of particles per liter. But ultimately, I want to talk about percent NaCl. So I'm going to have to ultimately have grams of NaCl on the top and grams of solution on the bottom. So I'm going to have to take a few steps here. So first thing I can do, if I have moles of particles, I can convert this. I want NaCl. What is the conversion between moles of particles and moles of NaCl? Again, we're
Two
so yes, say it again.
2 moles of particles per 1 mole of NaCl.
Exactly. It's kind of what we were talking about a little earlier with this dissociation. The nice thing about doing dimensional analysis like this, if you're wondering, like, am I going to multiply or divide by this conversion? You just have to make sure that the things are in the right place to cancel. So the moles of particles cancel. So now I have moles of NaCl per liter. Now, I don't want to have moles of NaCl, though. I need grams of NaCl if I'm going to be doing percent solution. So I'm going to need another conversion. How do I convert between moles of NaCl and grams of NaCl?
So it would be the molar mass of NaCl over 1 mole of NaCl.
Exactly. So, and if you go on to the periodic table, normally if we're in the classroom, I just go up but it's just in the interest of time, I'll just say it's 58.5 grams per mole of NaCl. And again, you want to just think about what goes on the top, on the bottom, make sure things cancel properly. I'm going to need my moles on the bottom. 1 mole NaCl is going to be 58.5 grams of NaCl. So here I have this dimensional analysis. I have moles, NaCl, get rid of moles. So, and if I multiply through on this whole thing, what I'm going to end up with is, in fact, I will get my calculator. I get 0.3, 58.5 times 2 divided by, this is going to be 8, basically 8.8 grams of NaCl per liter. And now I need to change this into, I'm close. How am I going to turn this into percent NaCl? So I have the grams of NaCl on top. How much does a liter weigh?
Do you multiply by 100?
So first we need the weight. We need the weight of a liter. How much does a liter weigh?
Will be 1,000 grams, right?
Exactly, because 1 mil was a gram. So a liter is just going to be 1,000 times that. It'll be, so this is basically over 1,000 grams, right? Because it's 1 gram per mil. So a liter is 1,000 mils, so it's 1,000 grams. So now, and then to make it to a percent, you have to multiply times 100. So this gives me, if you multiply it out, and if we round that, it basically becomes 0.9% NaCl. This, I mean, it becomes 0.88, but it's basically, we just say 0.9. So does this make sense how I got to this number here? In order for my saline to play nice with the cells and not make them explode or shrivel, it has to be 0.3 osmolar. And if you just do the math from moles of particles to moles of NaCl to grams of NaCl and do the ratio of the weights, which is how we do percent solution, it's just all, that's, you get that. And if I go, let me find it for you. Just to show you, I am, let me share screen. This is just from a medical supply. Saline pre-filled syringe for flushing out an IV line. It's like, oh my God, 0.9% saline, NaCl. It's like, I'm trying to give you a sense that this is actually important to understand this and that it makes a difference. And this, 0.9% saline to flush an IV line someone didn't just pull it out of the air, right? This is about calculating what is the osmolarity that is going to be the same osmolarity as your physiological fluids. So does that make sense? So, so all this thing about an understanding whether or not something dissociates or not is important. Like if you were doing the calculation for doing some IV drip of glucose for somebody, like what is the concentration of glucose to put into their veins to give them some energy? And you do that whole calculation, there's a whole different conversion between particles and moles for glucose compared to salt, right? So you could calculate what is the appropriate percent sugar, but you'd have to know that sugar doesn't dissociate, whereas the salt did dissociate. So I guess I'm just trying to make it feel more more real. Like all this stuff actually has implications on the clinical sides of things. It's not just like, okay, we got to learn these things. It makes a difference in figuring out like what are you gonna push up and clear their IV line with. So, boop-a-doo. Um, so any questions about that?
So quick question. I didn't have the calculator. So we got 0.88 and then we just rounded up to 0.9.
Yeah, 0.88 is basically
Okay,
0.9.
just rounded up. Okay. Thank you.
Right, and yeah, this is as good a time as any to actually I should go to the let me go to back to the other screen. Uh-oh, hold on. There we are. And give me a few moments here. Okay. I'm going to share my screen again. All right, I think where I put it here under remote lecture week 2. I am going to make this visible now. I'm just publishing it. So it's when you look next, it will be there. Chemistry review homework. So it looks like this. It's a PDF. And basically what I'm going to want you to do is print it out. And then you're going to scan your answers and you'll put them in, you'll submit them, as a PDF. But, basically it's just 15 points. You're going to have a week and a half to do this. If you have questions about any of this, you ask. Or you can look it up. You can ask me. There is no reason you should not get 15 out of 15 on this chemistry homework. But it is important. I don't want you just to find something and just write it without thinking about what you're writing, because then you're not actually understanding it. So make sure whatever you answer, you actually know. Don't just mole, let me just copy verbatim the definition of a mole, but not actually understand what I'm talking about. So that's the danger. So don't do that. Make sure if you write what is a mole, make sure you understand what you mean when you're saying what is a mole. Here, this is actually just kind of includes some of the same stuff we've been talking about. Given that physiological fluids are 300 milliosmolar, here it says, what is the molarity? If I wanted to find the molarity of physiologically isotonic glucose, how would I do that?
Could use dimensional analysis like the other way that we were just doing.
Yeah, we could do dimensional analysis again, except we wouldn't have to go as far at all because we're still staying in moles. As soon as you go from moles particles to moles glucose, you're done, right? So, and actually, given what you know, without even doing dimensional analysis, what is the relationship between molarity of glucose and osmolarity of glucose?
1 to 1.
It's going to be 1 to 1. So your answer better be, an equivalent number. So play around with that. Anyway, this is going to be due. Where do I have it right here?
The 10th, I think.
Yeah, the 10th. I have it due the 10th. So, so you'll print that out, you'll fill it out, you'll then take a picture of it and submit the PDF of it, and I'll grade it that way. And again, if you have trouble with it, just ask. So that is that. Okay, this is also just remembering for all of you that kind of missed it, there's a warm-up again that is going to be for Thursday. So make sure that you do the warm-up before the class begins. All right. Let me go. Let me go back over here. So one of the things that there is on that homework that I didn't mention that I should mention just briefly here, the idea of equivalence. So in our class, we're not going to really use equivalence, but they are used to specify solutions in clinical settings. Like if you're looking at the dialyzing fluid that you're using in, kidney dialysis or something, they'll talk about milliequivalents per liter of like potassium or something. So I want you to know what this word means because it'll show up. When you're in a more clinical setting, you'll see concentrations expressed as equivalents per liter. So just for completeness, this will be on that homework, but it's not going to be on a test. Equivalence. This is one equivalent donates 1 mole of either positive or negative charge. So it can get a little confusing. So if I had 1 mole of sodium chloride, because this breaks apart into 1 mole of positive and 1 mole of negative, since it's either positive or negative, this would just be 1 equivalent. If I had 1 mole of calcium chloride, that would be 2 equivalents. It just has to do with how many ions are getting sent into. Acids can get specified with this as well, anything that has ions. Equivalence per liter is normality, which you probably have seen in chemistry. That's often how acids are expressed in normal. But again, sometimes you'll see things expressed in normality or in equivalence per liter or something like that. So you should know, like in that context, equivalent means basically one equivalent is something that is adding either 1 mole of positive or negative charge. So, and like I said, this part, osmolarity goes so deep in our class. This does not go deep in our class, but I do want you to be exposed to it because it does show up in clinical settings, and you don't want to look at it and like, what is that? That way you can say like, oh, I know what that is. So, okie dokie. What else do I have here? 10:44. All right, so what we're going to do now is back to chemistry review lab. So, are there any questions about parts 2 and 3? As people, I'm sure, hopefully, people have started working on your discussions and things for that. Are there any questions about the main take-home messages for the parts that we've done so far? It's all, they say, clear as mud. All right. So now we're going to do part 1, which is looking at pH. So we need to spend just a little bit of time making sure you remember what pH is. There are different ways of specifying pH, but for our purposes, we're going to say this. pH is minus log of the hydrogen ion concentration. It's worth spending a few moments looking at the actual math because it makes a difference in interpreting and understanding how pH moves and does what it does. So again, these brackets, this just means hydrogen ion concentration of our solution. Log, what is log mathematically? What does log mean? Anybody know? Somebody's
How do you solve for an exponent?
Yeah, so in particular, the exponent on what number?
10.
10. So 10 to the log x equals x. So it's basically saying, what power do you have to raise 10 to give you x? So if I had, what is the log of 10? What power do I have to raise 10 to give me 10?
1.
1. If I say log 100, what power do I have to raise 10 to give me 100?
10. I
Two.
mean, wait.
2.
If log 1000, we're going to 3. If I 10 to the third. So the thing to be aware of here is as this log thing goes up in a linear fashion, it's describing something that's going up exponentially. So when I have something that has a pH that is, 2 lower than something else, it's actually got 100 times as much hydrogen ions. If I have a pH that is different by 4, it means the concentrations are different by 10,000. So just kind of keeping that in mind, that it's a logarithmic scale, which means that it's very nonlinear. Also, this minus sign, this means that everything's going backwards. As my H plus is going up, the pH is going down. So that is worth paying attention to. As we have lower and lower pH, it means it's a higher and higher H plus concentration. So let's think about just water, distilled water. So H2O, and it's just sitting there. It's got, and it's not at absolute zero, it's got that energy, that vibrational energy, rotational energy. All these bonds are pushing and pulling and twisting on each other, and things are they're whacking against each other. Every once in a while, they break. So every once in a while, these break apart into an H plus and an OH minus. And just for completeness, I should say, if you're in a more formal chemistry class, you won't actually talk about free H pluses. You'll talk about hydronium ions and blah, blah, blah. And even there, don't worry about that. For our class, we're just going to, approximate and say, oh, there's a hydrogen ion floating around. So H2O every once in a while breaks apart into H plus plus an OH minus. But then these guys are running around whacking to each other and reassemble and become an H2O again. So we have this constantly. H2Os are breaking apart. H pluses and OH minuses are reassembling. And obviously you realize if you look at water, it's mostly water. Most of the water stays as H2O, but there's always a small amount that's broken apart. So in distilled water, the concentration of H plus is around 10 to the minus 7. So this is just kind of normal water. This is the concentration of, so this is at equilibrium. When water is just sitting there in the glass, there's a small, very small, again, this is 10 millionth, right? 1 out of 10 million. So it's very small, but there is a small amount of these that are actually broken apart. What is the pH for this? Remember, pH equals minus log of the H plus ion. H plus. So remember, log is what power do I have to raise 10 to give me this? Again, that's not rocket science. What power do I have to raise 10 to give me 10 to the minus 7th?
7.
Exactly, 7. So this is minus 7. So the pH of this is 7. So this is kind of our neutral water, right? Just the water at rest. There's a small amount that has broken apart. The concentration of the H plus is 10 to the minus 7. So it makes the pH 7. That's what we call neutral. If you increase the amount of hydrogens in the solution, and there's different ways you can do it by adding acids. Let's say I add enough H plus, so now, remember it was 10 to the minus 7, but let's say I'm making it 1,000 times more. I'm going to go 10 to the minus 4, right? This is 1,000 times higher than 10 to the minus 7. What's the pH of this? This is 1,000 times more H pluses. What's the pH here?
4.
Yeah, pH is going to be 4. It's just minus 4 or minus. So notice what's happening. As H plus concentration goes up, pH is going down. So the more hydrogen ions you've got, the lower the pH number is. We also say this is more acidic. So people get confused. Even up to the very end of the class, people miss questions on this. And it can be confusing. You really not need to keep these numbers straight. Again, pH goes down when hydrogen ion goes up as acidity is going up. Notice also it's nonlinear. If I have a pH 7, it's neutral. pH of 6 is 10 times as much H plus. pH of 5 is 100 times as much H plus. pH of 4 is 1,000 times as much H plus. So that's where this log comes in. So it's this very nonlinear relationship. So this is getting more acid. We can also take away H pluses and make less H pluses. The way we usually do that, by adding hydroxyls. If I start adding hydroxyls into my mix, they will mix with the hydrogens around and become H2Os. So by adding the hydroxyls into my solution, my H plus concentration overall is going to be going down, right? So here I'm adding my little hydroxyls. The overall H plus is effectively going down because the H pluses are combining, the free H pluses are combining with the hydroxyls and turning into waters, which just become more water. So let's say my pH went down by, or let's say H plus concentration, which again we said is normally minus 7, or 10 to the minus 7. Let's say it went down by 1,000. So now it's 10 to the minus 10. 10 to the minus 10 is 1,000 times less than 10 to the minus 7. What's the pH of this thing?
10.
10. Right? Remember, it's just minus log H plus concentration. So power I need to raise 10 to make 10 to the minus 10 is just minus 10. Minus minus is a plus. So pH. So here, pH is going up when H plus concentration is going down. Our acidity is going down. But we are saying the alkalinity is going up. Or we also say that it's becoming more basic. So when you're looking at this over the weekend and reviewing it, make sure you really get solid about what goes up and what goes down in these different situations, because pH is going to be important through the whole semester. And we'll be talking about pH in terms of buffers like we're talking about now. We'll be talking about it in terms of in the respiratory system. We'll talk about it all over the place. So you want to really get this idea of pH going down means acidity and H plus is going up. pH going down up means more alkaline but less H plus, all of that. So, and again, it's especially if it's stuff you're not as used to, it can get kind of confusing. Like, whoa, up, down, what's going on? Just write it out, make a page for yourself and kind of describe it well so you can see all the relationships. So any questions about what pH is actually a measure of? At least, and again, there are different ways of approaching defining pH, but for our purposes, this is it. So the pH in the body is usually around neutral, typically actually more around 7.4. When we talk about homeostasis, this is an important thing that we have to keep stable. If your pH starts going up, you're going into alkalosis. If your pH starts going down, you're going into acidosis. If you go too far in either direction, you're going to die. So there are a whole lot of different mechanisms in place in your body to try to resist changes in pH, to stabilize your pH. The first order are these things known as pH buffers. So something is adding some acid into your body fluids or adding some hydroxyl, something alkaline, changing the pH of your body. These buffers are going to respond and pull it back into the safe zone. That's what our lab today is about, is looking at buffers and getting a sense of how buffers work and seeing that they do work even. So that is what this pH buffer is. It's something that resists changes in pH. Hold on, yeah. So I can show you if I've seemed like a little off today. I've got I don't know if you can. That's actually doesn't really show up here. Ooh, no, I can't.
Some good bruising going on.
It's where I've got like a really bad hematoma right now. I can barely, if I try to bend this arm one way or another way, it just like an ice pick in my arm. It's yeah, so I actually will end lab slightly early because I have like an online Kaiser appointment before the lab is all the way done. But pH. Let's talk about how different kinds of acids. So, acids. Think about HCl, hydrochloric acid.
Professor,
Uh-huh.
I have a question. So what are examples of some things that can change the pH of the body? Would that be like
I'm
food
showing you right now.
that we- Okay.
That is exactly what we're going to show right now. So strong acids. A strong acid is something that dissociates completely. So HCl, you put it into water, becomes H plus Cl minus. So if you are dissolving HCl in water, you are increasing the amount of H pluses around. And things are becoming more acidic. So this is, there's lots of things, different acids that do this. When they go into water, they dissociate and release free H pluses, and those H pluses then are making the pH go down or the acidity go up. You can also have strong bases. Like potassium hydroxide. You put this into water and it dissociates into potassiums and hydroxyls. And like I said, the hydroxyls then combine with the free H pluses to become H2Os. So overall, the amount of H plus is going to go down. So a strong base dissociates completely to release the hydroxyls, which then take the H pluses out of the solution, and it goes down. So, but then you also have what we call weak acids and bases. And the weak acids and bases are going to be the key to the buffering systems. So, do not completely dissociate. So, example, carbonic acid. We're going to see carbonic acid a bunch in this class. H2CO3, when you put it into water, it breaks apart into H plus HCO3 minus. This is a bicarbonate ion. But it doesn't dissociate completely. So it's in equilibrium. Some of it is staying intact as just an H2CO3. Some of it has broken up into individual ions. Right, so does this make sense? It's dissociated, but not completely. Not completely dissociating. Some of it is staying intact, some of it has broken apart. It's an acid because it's donating H pluses, which is going to increase the amount of H pluses. But it's going to do something really interesting in terms of being a buffer. So this is a critical part of buffers. Like these weak acids and their conjugate bases are going to be at the core of these buffer systems, and it works like this. So let's just, it's easier to think of if we just think about like half of it right now. Look at this half of it. So let's say I start adding in, let's say I kind of going back to my, where did I, no, that's not what I was looking for. Oh, hold on one second. Sorry about that. All right, so where did I write? Here it is. Strong acid. Let's say I have HCl that I'm putting into my solution, which is adding a bunch of these H pluses. So I go back to here where I'm adding in all these extra H pluses. What that is going to do, by increasing the concentration of the products on this side, it is going to force the equilibrium to move in this direction. So what's going to happen is a lot of these extra H pluses that are going to be added in are going to combine with the bicarbonate ions and just make an increased amount of H2CO3. So basically, if the acidity goes up by adding H pluses, this equilibrium moves this way, which then reduces the amount of H plus, brings the pH back up, right? So if the pH goes down because you're adding H pluses, this equilibrium shifts, which brings the pH back up. If you added a strong base, you're going to get similar but different. Let's say, oh, you goofy. Let's say I add a bunch of hydroxyls. Those hydroxyls are going to combine with the H pluses, and the H plus amount is going to go down. When that happens, more of this will dissociate, and this equilibrium is going to move back in this direction and increase the amount of H pluses there. So no matter what you do, if you take H pluses away, this thing will move to the right and add in H pluses. If you add H pluses in, it will move to the left and take them away. So the basic idea here is no matter what you do, this thing is going to respond in a way to bring you back to where you started. And that's kind of the definition of a buffer. It's resisting changes in pH. If the pH is going up, it brings the pH back down. If the pH is going down, it brings the pH back up. And it kind of is almost instantaneous. Obviously, it's going to be limited by the sheer amount of the weak acids and bases that are lying around to actually take up the slack. But this is, we're going to see a variety of different versions of this as we go through the semester. There are phosphate buffers, the bicarbonate buffers, even the proteins in your cells act as buffers. So does this basically make sense? Gesundheit page. Any questions about what I'm talking about here? Okay, so let's look at the lab. I'm going to go share. We go down, down, up. Back to the chemistry lab. I should, hold on. Let me get the... Where did that go? There it is. Okay. Chemistry review lab if you take a look at what it says here, let me view, let's do single page. So it's basically talking about, in this case, we're using a phosphate buffer rather than a bicarbonate buffer, which I just described for you. But we're going to have a buffer solution, and there's like just recipes you can use how to create them to be stable at different pHs. The one that we made for this lab is stable around pH 7. And basically what we're going to do is just use a pH meter, which you just stick in the solution and you can see what the pH is. And you can then look at how does regular water respond to adding little drops of acid and base. And then do the exact same thing with a buffer and see how pH changes. So basically, the basic idea, actually let me just stop sharing. It's like on one hand, you're going to take a beaker of distilled water, drop by drop, add in the base and the acid in the base. And what's going to happen to the pH as you do add drops of acid to the water?
It's going to go down.
It's going to go down. And then when we start adding base, what's going to happen?
It'll go up.
You go back up. And then we'll do the exact same thing with a buffer. What would you expect to see if we're using a buffer instead of using distilled water?
Little or no change.
Exactly. Little, by definition, that's what this buffer is supposed to do. It's supposed to resist changes. It should just stay pretty stable. So we'll find out. Last thing I should mention, when you know that you are going to be taking data, it usually is a good idea to make a nice little chart in your book ahead of time where you can write it in and keep things neat. So for instance, you're going to start with distilled water, drops of acid, and again, one of the things that's nice about having the notebook that has the graph paper in there, you can make little charts really easy. So doing something like this ahead of time actually makes your life a lot easier. So make graph or make table before collecting the data. Assuming that you know the procedure, you're going to be adding drop by drop and recording the pH. So put this ahead of time, make it pretty. That way, as you get the data, you'll have a place to put it. For the lab right now, you're going to watch, I forget if it's me or Tina is going to be, I think Tina is doing the little drop by drop, and you will actually have to record the numbers off of your YouTube screen. But it makes sense. Like I'll help you. I'll kind of set you up before we start. Give you a chance in your lab notebook. You're going to want to have space for the instructions, which are, from the lab book. That's part 1 buffer system and has a procedure. That should be first. Then the next section where you have your data, you make a couple little tables. There's going to be one that you're going to use for the water, and then a similar one that you're going to use for the buffer solution. And then as the data comes up, you'll have the perfect home to record the data as it shows up on the screen. Does that make sense? Like a little bit of thinking ahead can keep things way more organized. You know what the data is going to look like, and having a little home for it to land means that it's going to be really easy to keep track of it and what it was and what the conditions were. All right, yeah, that's right. These were the distilled water and these were the buffer. This is the base and this is the acid, la la la. So, all right, let us continue along. I'm going to share screen again. Doing the chemistry lab. Again, I put all the doing in little quotes because obviously, again, I feel bad you're not doing it, but you get to see us doing it. All right, so I'm going to start with part 1 here, steps 1 through 4, which is basically the part where you're doing the experiment with distilled water. Then after that, we'll do the exact same procedure, but instead using a buffer. So let's go and watch this. Oh, don't you dare be stuck. Come on. You little... All right, I am going to have to restart something. Hold on a sec. Shit. Excuse me, it's going to take another few moments because of all this two-factor authentication, which is always such a pain in the... I don't know, you've probably noticed that you don't go anywhere. You're just looking at the same website 2 minutes after you just looked at it, and all of a sudden it says, "Who are you? Don't know who you are. Please do this whole rigmarole." My apologies for our technical difficulties, and here we go. We are now continuing with our regularly scheduled program.
All right, so we're going to do the chemistry lab today, and the exercise I'm going to demonstrate is we're going to investigate how pH is changing in a solution of water and a buffer as we add a strong acid known as hydrochloric acid, and followed with adding a strong base, sodium hydroxide. These are the pages that have the instructions, and it's totally okay for you to glue all of this into your lab notebook. Sometimes there is helpful kind of background information in the introduction. If I were a student, I would totally glue this in. All right, so we poured some water into these 150 ml beakers. And so a beaker isn't a very exact measurement device, but for this exercise, we just need approximately 100 milliliters. So it's more important that you have the same amount in both of the beakers. So I have 100 milliliters of distilled water in this one, and I poured some of this buffer, and so I poured 100 milliliters of buffer in here. But we're going to start off taking a look at how pH changes in this water as we add acids and base. And so what I have here to measure with is a pH meter. So sometimes students are really gung-ho on starting and they start using it this way, but you do need to remove the cap for this to work. And so if the pH meter is very off when you stick it into the distilled water, so distilled water should technically be pH 7. If it's completely off, you can go and do a calibration or ask your teacher to help you calibrate it. However, the main idea behind this experiment is not so much to be super exact, more showing what is happening when you add acid and base into water versus what's happening when you add acid and base into buffer. So it's more a relative comparison. So to turn this on, there's an on-off button, and so I have already turned this on, and then you dip the white probe into the water, and it will blink, and it can take quite a while for it to stabilize. And so we'll wait about 30 seconds at the most. Oh, now we shut off, so I'm going to turn it on again. We'll wait 30 seconds, and then whatever it says after 30 seconds, you can record that into your lab notebook. All right, so in this case, my starting point is...
All right, so what I would, given that you can just do this along, this is going to make sense to just, I would say right now, if you have your lab book in front of you, just make a little table like I just showed you. Make a little table where you are going to record. This is 0 drops of acid is going to be 7.55. It's going to be the first data point. Then you'll have the next little place for 1 drop of acid, 2 drops of acid, 3 drops of acid. So you know the procedure. So make a little table right now. I'll just give you a few moments. You kind of want to get into the habit of what is it like to kind of get ready to receive the data.
So for like the columns, we would put H2O, distilled, and buffer pH on both of them.
So there's more than one way to do this. There's, the way I showed you when I was a few moments ago, you could just have 2 tables, one for water, one for buffer, and then as you go down, like drops of acid, and then after I think after 5, then go to the drops of base. But there's no, there's more than one way that would be correct. As long as it's clear, then that's fine. And again, make sure if you haven't pasted in the instructions or the methods, make sure you leave a little space before you have where your data is recorded, because it's nice just for a flow to have the methods before the data, because you see what you're doing and then you're doing it. right. Has everybody got that, or are people still going? Does anybody still need a little more time? All right, so we're going to play through this. This is going to go for the next few minutes. I've edited it so that whenever there is a number that you need to pay attention to, I have this little like kind of reverse sun rays coming in to make you see like, whoa, there it is. The reality is the pH meter drifts. It's usually has trouble finding a real stable value. We don't care. It just needs to be ballpark. If it's 7.5, 7.55, then 7.56, then 7.57, then 7.58. Just like write down 7.55 or whatever, because that's we're worried more about big changes. We don't worry about changes of 1/100th of a pH, and this thing tends to not stabilize. So just any of the numbers it says while the big kind of rays are around it, that's a good number for that condition. All right, so we're going to continue. Again, you should be writing in pen. If you remember, your lab notebook should be in pen. And we are going to continue with our data gathering. So this was with nothing. This is just distilled water with no acids or base added yet.
I'm going to record this pH in my lab book because this is my baseline. And so I'm just going to make a record of that. So I'm going to put 0 drops equals DI water, distilled water. And then I'm going to write down what the pH is. So that is my baseline. Note that I have also already made a table to put my data in. This is really important. It's good practice because one, sometimes you don't have time to write this as you go along. And two, this makes a lot of sense because it shows you and me that you have read the procedures, you understand the procedures, you know what to do. And so I have a column here for my water beaker and I have a column here for my buffer beaker. I have indicated that I'm going to add 5 drops of acid to the water, and then I'm going to continue with adding 6 drops of sodium hydroxide, my base. Then we're going to repeat the whole experiment with the buffer, and so I have another table written out there, ready to go. All I need to do is record my pH on the meter.
Right, and I think it was Brittany was saying, there are more ways to do it. Like if you wrote just one side that was number of drops, and then on the other side was pH in distilled water and pH in buffer, that would work too. This is a nice, clear way to do it, but it's not the only way to do it, right? There's just kind of putting it out there. There's a wrong answer. There's a wrong way. If you write something that's totally confusing or not connected to the actual methods, but there's not like one right answer. So that's in terms of how to lay things out clearly.
Column here for my buffer beaker. Another table written out there, ready to go. All I need to do is record my pH on the meter. So in this exercise and in this video, we want you to record whatever the pH meter is saying into your lab book at home. So at this point, we're ready to go. I'm going to put this probe gently. Sometimes pH probes are very sensitive, so always handle any equipment gently. And then we're going to start off with our acid. So here I'm going to add 1 drop. And I'm going to stir. And then we're going to see what the pH is. And we'll wait a little while. And then I'm going to record in my lab notebook.
Right, and like I said, notice there were numbers shifted. You just want any of those numbers is fine. Those all differ by like 1/100th of a pH unit. So don't worry, just any of those is fine. The actual relative changes we're going to look for are way higher than anything that makes any difference for. So any of those numbers that shows up while it's being highlighted is a fine number to record in your lab notebook.
I'm gonna put it here. All right, I'm gonna add so second drop. Stir and we'll measure. And record. We'll add our third drop. Stir. And measure. And record. Our fourth drop. Stir. And record.
So if you angle it, there's a reflection. That's better.
And I'm on my last fifth drop. All right. And record in your notebook. Next, we're going to switch to our sodium hydroxide, which is a strong base. And I'm going to add 6 drops, but one at a time. So drop 1. And it looked like I got 2 drops there, so I might actually have to skip that data. But the thing is that we're collecting class data. And so my data, even though I don't have a drop 1, I only have a drop 2. I'm going to just put a dash in my data, but because all the other groups have data, chances are that they didn't do 2 drops there. And so we can average these numbers together.
Right, so this is important. I mean, this, we kind of had this Gumby when we were trying to get this going, but we realized it's useful as a kind of learning moment here. It's like there were 2 drops. She doesn't just pretend it was 1 drop, because otherwise the data isn't true anymore. And also when we compare it to other groups, it doesn't compare equally anymore. So in her lab book and in your lab book, right now for the first drop of the base, you should just put like a dash. You didn't get any data. We don't know what the value is. We'll never know what the value is because that moment has passed. So when we measure the pH here right now, this is going to be the pH for 2 drops of base that you've now added into that beaker. So in your lab book, your little table in your book should reflect that. Does that make sense? And this happens. This is, we kind of left this in too, so you can see that everybody's human. Everybody tries to do their best and messes it up sometimes. But you just need to be aware of what's going on and adjust appropriately.
In our spreadsheet. And so for my drop 2 then, I'm going to record.
What are the chances? Drop 2, 2.22.
And then I'm going to add drop 3.
Tilt it towards me. Thanks.
And drop 4. drop 5.
Tilted again. Yeah.
Record. And my last drop. And record. Okay, so now I'm going to switch to buffer. So I'm going to clean off the probe. Just rinse it off. Make sure we're not having any residues to influence our data in any way. And we're going to switch to our phosphate buffer.
Okay, so what did people notice as we added drops of acid and base to the distilled water?
One that we just did, there was not big jumps until that drop 6. So we went from 3.31 to 9.50.
Right, and think about the other side. What was happening when you were adding the acid? How did the pH move?
Well, it moved down, but still not in those, like in that big spike, even at like drop 5, for example.
What was drop? What you started at 7, about 7. What was the first drop of acid?
3.37.
Yeah, it dropped by like 4 on the first drop. It went from like 7 down to 3. And then what did it drop from? How did it go from drop 2 to 3?
It moved down another level of pH, but it kind of stayed in that range.
Yeah,
It wasn't like another big drop.
didn't change. So this has to do with the nonlinear nature of the logarithm. Here I think this will make this clear. Let's use just regular numbers. Let's say there were 10 H pluses in here. And let's say each drop here has 1,000,000 H pluses. Actually, let's say 10,000 because that's the level of floor. So let's say there's 100,000 here. So there's 100,000 H pluses in this drop, and there's only 10 H pluses in my beaker here. So the first drop that I add, it's increasing the amount of H pluses, by 10,000 times, right? From going from 10 to, once I add that in, I'm at 100,010 basically in there. So I went up 100,000, which is a pH dropping by 4, like going from 7 to 3, right? Now let's say I add the second drop, which, and let's say each drop has 10,000 H pluses in it. I'm sorry, 100,000 H pluses in it. So now I add the second drop in there. Now I've gone from 100,000 to 200,000. So now it's just gone up by, oh, how boring. It went up by 2. I've doubled it. Right? So the first drop, I went up by 100,000, which was at 4 pH units. The second one went up only by 2, which is just a fraction of a pH unit. Right? So you see how that nonlinear aspect of the logarithm really changes how, if you were like looking at, if you drop by drop by drop, just looking at the amount of H plus, it would just kind of go up linearly. Each drop adds more and more H pluses. But if you're looking at the logarithm, it's going to be some crazy, like, actually, yeah, forget my graph there. But basically, it's not going to be linear at all. So if we go back to here, like my third drop where I add another 100,000, I'd go from 200,000 to 300,000. Now I've only gone up by like 50%, not even 2 times. So each time, or actually I should take that back. I've gone up by 2 to 3 of, yeah, I've gone up by 50%. So each time I add another drop, it basically goes up by even less of a fraction, because I just keep adding a linear amount with each drop. So that's why this pH is very nonlinear. Each drop, the first drop that you add, the pH is gonna go up a lot, and then each successive drop, it'll go up a little, and then when you start adding the base, it's going to bring it back down until you hit that kind of place where boom, it comes back down or up. I mean, actually, it should be going, say this is 7, back. It basically started here. First drop went down, but then it goes really low, and then it comes up, and then you add the base, and it comes up really slow until you hit that place where boom, it jumps back up. So it all, yeah, so if, I don't, does this make it make more sense?
Yes.
Okay. All right. So what we're going to do now is the exact same experiment, and you saw it shifts. It went from 7 down to 3 up to 9. And in fact, we'll see in a little bit the class data from other groups as well. You can see the averages across many groups to work with for your write-up. But right now we're going to do the exact same experiment, except instead of putting the acid and the base into distilled water, we're going to put it into a buffer, a phosphate buffer solution. And again, the big point of doing these labs is just so you see things with your own eyes. Like, what you're going to expect. What a buffer is. We have the definition. But it's kind of cool actually watching it happen in real time. And then Brittany, I can also, like, if you need to go back later, these videos are always there in the module. So if you don't get a response, you can always just go back and look at the video as well. All right, so we're gonna share screen. Back to here. We're gonna go back.
So next we're going to investigate how the pH is affected when we're adding the acid and the bases into a buffer. And so this is a phosphate buffer, and we'll need to get our baseline first. And so we're going to get our baseline reading. I'm going to record that into my lab notebook. It's a little lower than it should, but as I said, we're trying to demonstrate more a relative relationship and compare the two fluids. So I'm going to record this now. And then we're going to start our experiment. And once again, we're going to start with the strong acid. So I'm going to add 1 drop. I'm going to stir. I'm going to measure. And I'm gonna record. I'm gonna add another drop. Stir. And record. We'll add another drop. This is drop 3. Stir. Oops. And record. We're going to add our drop 4. And measure. And record. And this will be the last 5th drop of acid. And measure. And record. And now we're going to switch and we're going to start adding our sodium hydroxide, our base. Drop 1. And measure. And record. Drop 2. And measure. And record. And drop 3. And record. Drop 4. And record. Drop 5. And record. And our last drop of base. And our last measurement. All right, and so next you're gonna go over to the computer in our lab and we're gonna enter your group data into our Excel spreadsheet. And then your instructor would upload the whole Excel sheet to Canvas, and so you can graph things and draw conclusions based on the data you see from this data. Last note, when you're adding acid and base together, you make water and salt. So when you're disposing of this, you can pour it down the sink. And finally, because these are strong acids and strong bases, you must wear gloves and safety goggles to protect your eyes.
All right. So, what, just without even thinking too hard about it, did you notice any Any big differences between the water and the buffer?
There was no significant drop or rate rise in the buffer. It kind of all stayed in the 6 point something range.
It stayed. I mean, it moved a little bit, but not much.
Yeah.
So, why is it important? Like, why is it important that we have these buffers in the body? In your discussion, you want to talk about how the buffer and the water differed from each other, but you also want to kind of tie it into the larger themes of why do we care? How is this related to physiology?
It's important in remaining or maintaining homeostasis, right?
Yeah, absolutely. So this is going to be an important tool in your body maintaining its pH homeostasis. And we talked about just in lecture today, what's one of the important reasons to keep your pH stable in your body?
Drinking water.
What's that?
So the body can work properly. So proteins won't get denatured.
Yeah, exactly. So we don't denature proteins, so the enzymes are functioning properly. It's just one of many things, but this idea, there's a lot of physiological processes, particularly your metabolism is going to not work if the pH doesn't stay in that sweet spot where the enzymes have. Remember, enzymes only work if the shape of the active site perfectly matches the substrates and they bind properly. That's an important thing to remember. An enzyme has to bind its substrate. And if it doesn't do that because the shape is messed up, which can happen due to pH changes, then the chemical reactions won't run. So
we can say, so we can say enzyme must have a normal shape in order to work properly.
The enzyme has to have its appropriate shape.
So next we're gonna invest.
Yeah, and if pH is not stable, then the enzymes get denatured and they no longer function properly. So I'm going to share screen again. So there's part 1, the buffer systems that we just did. Part 2, the electrolytes that we did last time. And at the bottom of this page of this doing the chemistry review lab, there is a PDF. It says, here is the Excel file that includes class data for part 1. So, and there are a number of different labs that include both raw data as well. So there are a number of different tabs. Let me just show you how this works. So this is going to be the first one you're going to see, but we'll see lots of things like this as the semester goes on. Hold on, what's going on? All right, there's something weird here, but I'm going to figure it out. Oh, there it is. Okay. So first thing that you're seeing, let me zoom down a little bit. First thing you're seeing is there's a bunch of different groups. Here we have 4 different groups. This is for distilled water on the top, buffer on the second part. It's saying what was the pH measured at 0 drops, before we started, 1 drop, 2 drop, 3 drop, 4 drop, 5 drop, and then here's the base drops coming back up. And then this line here is the average of the different groups. So it's always useful to look at more than one group or do the same experiment more than once and make sure that your results are not some kind of fluke. Like you trust things much more if there's repeatability. So here we have a lot of people doing the same experiment and seeing very similar things. And then we're averaging all of their results to get on average, what do we see? And again, we see on average, it starts around 7.4, drops down here to 1.6, zips all the way over here to 11.1. if you average across all the groups. With the buffer, it started at 7. Lowest it ever got was 6.6, and it got back up. So total range was about 0.4. For this one, the total range was between 1.5 and 11, so like almost 10. Right? So in your lab write-up, in addition to your personal data, you also want to have this group data here. And again, you can just, you can go into page layout, set print area, and you can like print this thing out. You can cut this out and you can paste this in your lab notebook as the group data. And you have to label it. You have to say like, this is figure 1 or whatever figure it is. And then in your discussion, you can say, as we see like in figure 1, our results that we saw on the YouTube video are consistent with the results that the many different groups got when they did all did the same experiment. And so you can bring these numbers into your discussion as well and compare your one example that you did with the data from many different groups doing the same thing. So that's again, in science in general, you just seeing something once is just anecdotal evidence. It might be interesting, but doesn't really tell you anything that you can really lean on until you see a lot of people getting the exact same results, or you do the same experiment again and again and it keeps happening in the same way. So just because you did it once and you saw it, you don't give it as much credence, as much trust. But when you get more, again, I'm saying it again and again, but it's an important point. So
you want us to print that out and paste it in our lab books as well?
Yes, you should. And then incorporate it into your discussion. Incorporate the fact that your data was consistent with the overall trends we saw across all the different groups.
I just had a question about the base drops numbers.
Uh-huh.
Like for what we just did, like the 4 and 5 in the water, I have like 2.49 and 3.31, but on that table it's like 10.3 and 10.9.
Right, but if you look, different people, like notice this person here went from 1 to 8.3. This person went from 2 to 2.4. Right, different groups are different. I think a lot of it has to do with inconsistencies in the size of the drops.
Oh, okay.
I think the difference between these classes and the stuff, I think some of the reagents might have been mixed differently. So there's lots of sources of variability in this, actually. We don't have to worry about it. But this is why even people are trying to do the exact same experiment with the exact same stuff. You get different details, but the overall trends are all the same. So we can trust the trends, even if the detailed numbers from one drop to the next might be different from group to group.
Thank you.
Most of these sheets are going to have another tab that has some graphs. I put this here because I want you to trust this idea that even though pH is very nonlinear, pH went 7.4 to 2.9 to 2 to 1.8 to 1.6 to 1.4, right? Here I basically calculated the H plus concentration as just, 10 to the minus log. It's basically the inverse of the log. And it's like, oh my God, it's basically going up linearly, right? So you don't have to put this in your lab notebook, but I put this in here just so you can see, like, even though pH is going kind of really catty, like 7.4 to 2.9 to 2 to 1.8, if you look at H plus concentration, it's actually just very regularly, each drop is adding a relatively constant amount by increasing it a constant amount. The other side should come down on a nice slope, and it doesn't. So that makes me think that somebody probably had a bunch of drops that they put in all at once that messed up the thing, and they just didn't realize it, or they were too ashamed to admit it. I don't know. But yeah, this downside should also come down at a nice slope. But again, the reason this graph doesn't have to be part of your thing, but I put it here just so you have a sense of a linear change in hydrogen ion concentration results in a very non-linear change in pHs. So blah, blah, blah. So comments, any comments, questions, or anything about all of that?
Mine's a little off topic, but for the graph, the group data that we just saw, when we do the ones that are actually like we do it in person ourselves, are we gonna at the end of the lab do that class data together and then be able to print that out? Or are we doing that on our own?
So say that one more time.
For the class data that we just saw, that graph that was just made, when we do the labs that we do together rather than just watching the recording, are we doing that on our own and printing that out, or are we going to do that at the end together, like so we get all the data together?
The data like that, most of the labs that we do, I will have an Excel spreadsheet like this that has group data that you can use in addition to the individual data that you're using. All right, so what we're going to do now, I just want to wrap this up by kind of getting you ready for the jumping lab. So in the jumping lab is the next lab, and this one you have to have an objective, hypothesis, and source of variability. So let's just spend a few minutes talking about the expectations for this jumping lab. And so what you need to have uploaded to, in fact, I can, I'm going to go back to share screen. I shouldn't have, not, okay. If we go back here, if you look under it says jumping lab, pre-lab. So it's the one right after chemistry lab. One just has the lab manual pages for the jumping lab. And then it has submit PDF of jumping lab pre-lab due February 3rd. So it's like due at midnight the night before class. I want to make sure that you do this before we do lab on Thursday. This is not a whole lab write-up. This is just like a half a page. But you do need to submit this PDF of your pre-lab before our lab on Thursday. And what is this pre-lab? Why, glad you asked. Now, you should remember from our discussions about the lab, this pre-lab, it's just going to be the beginning of the lab write-up. So this is in your lab notebook. It's going to be the objective, hypothesis, and sources of variability. Right? Objective, as we've seen, objective is just a sentence that says, is the independent variable related to the dependent variable? Hypothesis is your educated guess about what you think you're going to find. Sources of variability is just a list of things that you think might affect your results in addition to the specified variables. So this should only be like a few sentences and a list. This is not a major thing, but it's important that you think it through. So it's short, but it's concise. It has to, or I should say, it has to be precise. Like a number of people, I gave feedback in your little assignment that we did about making sure you're very specific about specifying your variables. For the jumping lab, I've talked about this a little before. I'll just review it briefly. We're going to take some measurements from a person. So we're going to take this subject. We're going to measure their height. We're going to measure their calf circumference. We're going to measure their weight. So here are these things that we have. And then we're going to have them jump. And we're going to see how high can they jump. And the way that the jump works is it's a relative thing, right? You measure how high are they when they are standing. How high do they get when they are at full extension as they've kind of jumped up? Right, so it doesn't matter if you're really tall and you barely jump off the ground, your jump is going to be very small because it's how high do you get above when you're standing, right? So does that make sense? When we talk about jump height, it's like how high can they jump relative to this baseline that they draw on the wall before they actually jump. They'll have a little pen. So they can like mark the wall before they jump, and then mark the wall when they jump, and then you can just see the difference. So independent variables, dependent variables. Before we get any deeper, what are the independent variables and dependent variables here? We want to see if any of these things can influence how high they can jump.
Weight, height, and calf circumference.
Are going to be what?
The independent variables.
Exactly. They're going to be the independent variables. We'll be using different versions of those, and then and we'll see. We'll have people of different heights, different calf circumferences, different weights. And then what are we going to do?
Have them jump.
We're going to have them jump. And we'll measure the jump. And what is that jump going to be?
The dependent variable.
Exactly. That's going to be our dependent variable. Right? So does that make sense? So independent variable, there's going to be, how many independent variables are there?
3.
Yeah, there's going to be 3. And how many dependent variables are there?
Just the one.
Just that one. So if you were going to write the objective for this one, what would the objective be?
To see if the person's height, weight, and calf circumference play a part in their jumping ability.
Yeah, so say that one more time.
Seeing if the independent variables, being the height, weight, and calf circumference, are related or directly related to their jumping ability or jumping height ability.
Yeah, so it's basically, does their height, calf circumference, and or weight affect their jumping ability or the vertical height that they can jump? And then what would be a possible hypothesis? Uh-oh. Did I lose him? Oh, shit. Are you guys there?
Yeah, we can hear
Yes.
you.
Yep.
Oh, all right. Because I'm trying to do. So I need to. So what are some hypotheses that are possible? I actually need to say goodbye in a second.
Somebody with
That
low weight and really tall, but decent cast circumference can jump really high. I don't know.
Right. So any hypothesis has to have the what you expect, but it also has to have the why. There always has to be a compelling, a reason. So
Because they're tall and they don't weigh as much, but they have good calf strength or good calf circumference, meaning good calf muscles, that they'll be able to jump high.
right. So maybe just make it a little simpler. You could say larger calf would be a larger jump because larger calf may have to do with, beefier calf muscles to jump more. Or
so we don't have to relate all three like at one time.
it doesn't have to be all three. It can just
Okay.
there's one that you think is the more, but it has to have a reason. It has to have a. You can't just say, I think people taller because they can reach higher. It's like, but we're doing relative. It does nothing to do with how high they are, how high they can reach. Could be they're taller, so they have larger muscles that are gonna generate more force against gravity. That would be okay. Or people who weigh less won't have to fight gravity as much and they can jump higher. Or who knows, whatever. We are going to calculate BMI, which is body mass index. It's just a ratio of their height and their weight, which is rule of thumb related to kind of their fitness and their kind of lean mass to fat mass. So it could be calf circumference is leg muscle, but only in people with healthy BMI, right? So I think the people with large calf circumference but healthy PMI will be able to jump well. Or who knows? There's lots of ways to go here. There's no right answer. So just kind of putting that out there. The only thing that is wrong is if you don't give me a what and a why that makes sense. So you have to have the what and the why, but there's lots of possible things that you could write here, and it doesn't have to be correct. We get the data, and it might be your guess is wrong. That's why it's a guess, right? So objective is just going to be, again, that simple. What's the relationship between the independent and dependent variable? Hypothesis, what do you expect and why? Sources of variability, what are possible sources of variability in this thing?
Well, we talked about if they're wearing shoes, but you said they're not wearing shoes, right?
But so yeah, types of shoes could be a problem, and that's why we're going to change that. We're going to make sure that nobody's wearing shoes. What are other sources of variability?
Your current injuries?
Injuries, yeah, that could be a big problem. What are other things that could affect anything that can affect their jump height that's not these would be a source of variability. What are some other ones?
Their
Like,
form.
The form, and again, we're going to control for that by trying to make sure everybody does it as well as the same as possible.
The kind of ground that they're jumping off of.
Kind of ground, yeah, that can make a difference. What other kinds of things?
If they're tired or not?
Yeah, their level of like alertness, tiredness, whether they just like gobble a handful of Adderall or who knows. So,
What about age?
I would say probably not as much of an issue. You could put that there, but I don't think that. I think that would be much less likely compared to anything else. But so you get the sense. So I apologize, but I actually do need to make this appointment, which is supposed to start any second now, and I'm in pain. So I really want to figure out what to do about this. So I am
Thank you.
All right, and so I am gonna get back into the Zoom meeting after this, hopefully, assuming depending how long this takes. So I'll be back here for office hours later this morning, but I do have to end this for this moment, and I will be free to answer questions a little later. So I'll see you.
Thank you.
Feel better.
Bye-bye.
All right, see you
Thank
later.
you.
Bye.